Hello. In this video, we will cover section 9.2, which is on the central limit theorem for means. In chapter 7, we introduced the central limit theorem for proportions. The central limit theorem for proportions told us that under certain conditions, a sampling distribution, which is the outcomes and probabilities when repeatedly conducting a survey, will have a normal distribution shape. This result allowed us to use a normal distribution to calculate the probability when conducting a survey. We then expanded that result to find confidence intervals and conduct hypothesis tests. But all of this was restricted to proportions. In this section, we're going to go through and we're going to expand that for means. If you're not sure of the difference between proportions and means, proportion is a percentage or a ratio, while a mean is an average. Okay, so let's look at some examples. Suppose we have a population of 1,000 people. 25% of the population are cat people. And you're asked to go through and find the probability that a survey of 100 people will have less than 23% cat people. Okay, so this would be a proportion problem. So these percents, okay, they're treated as proportions, okay? And the reason is because you could go through and you could take a percent, you could turn it into a proportion. Now, suppose we have a population of 1,000 people. The people in the population have an average of 1.2 cats. Find the probability that a survey of 100 people will have an average with more than 2 cats. Okay, this time, notice we've got average in here a couple times. So what we're dealing with is we're dealing with means. Okay, so that's the difference. This is what we did before with percentages. So you should right now have enough knowledge to go through and answer this question with the knowledge you gained from chapter 7. But you shouldn't have the knowledge to do this problem yet, and that's what we're learning how to do in this section and the one after it. All right, the sketch shows the distributions of in-state tuition and fees for all two-year colleges in the United States, right? So we've got some data here, and that data, they've plotted it for us in a nice picture. Notice that it is not normally distributed, okay? This is not a normal distribution. Now, it doesn't tell us how many colleges there are, but we're going to just assume that there are 1,000 just for simplicity and to make it kind of similar to the problems we just looked at. Suppose we went through and took 30 colleges from that distribution of 1,000, right? This would be a sample of the distribution. It's the equivalent of collecting a survey from the distribution, right? So you could go through and surveying. When you think of survey, you think of going through and talking to people, but what you're doing when you're talking to people is you're going through and you're getting pieces of data from a larger data set, right? That's the same thing as going through and finding a sample from a distribution. All right, so suppose we went through and found 30 colleges. We calculated the mean for those 30 colleges, and we got 3,425. Okay, so note there's a typo there. That should be 25. Now, let's say that we did that 200 more times, and then we wrapped that result into a picture with outcomes and probabilities. Okay, so we've got outcomes on this side and then probabilities are on this side. So you can think of relative frequencies like probabilities. Okay, so just for example, 0.04, that would be like a 4% probability of getting that outcome. All right, and so notice if you go through and you do 200 more samples, you get 200 different results. You plot them all together on the table. The one that we did is going to be right around here. It's going to be in this bar. Okay, so that bar looks like it has about a 5% chance of occurring. And then you plot it. Look what happens. We end up getting something that is normally shaped. Now, suppose you went through and used 90 college samples instead of 30 college samples. You get something that is even more normally distributed. All right, so this one is a little bit off, right? This one is less off. Okay, so in both cases, when we went through and created a sampling distribution of means, we ended up with something that was normally distributed. Okay, this is the exact same result that we got when we created sampling distributions for proportions. All right, and that's the result that ended up leading to the central limit theorem for proportions. All right, and so not surprisingly, we're going to have the same result for means. We're going to have a central limit theorem for means. All right, and here it is. So what it says is if we've got these three conditions, the first one is the same as for proportions, so you've seen that before. The second one is new. All right, so what does it say? It says either the population distribution itself needs to be normal or the samples need to be 25 or larger. So what does it mean by the population distribution? okay, that would be this. Okay, this is the population from which we were taking samples from. Notice it was not normally distributed. If it had been, though, right, we could have used samples that were smaller than 25 and it still would have met the conditions. However, since it's not normally distributed, our samples needed to be at least 25 in size, and they were 30 in size. Okay, so we did meet the condition for the central limit theorem. But yeah, so you either need to have the original population itself, so not the sampling distribution, right? The original population itself needs to be normal, all right? Or the sample sizes need to be 25 or larger. All right, and then the last condition is the same as for proportions. If you do that, then the sampling distribution that you'll get is going to be normal, approximately normal, with a mean that is the same as the population parameter mu, and a standard deviation that is the same as the standard error, which is given by this formula, where sigma is the standard deviation of the population and n is the size of the sample. One problem with this definition, the one that we just went over, is that it assumes that we have the standard deviation sigma of the population, also assumes that we have the mean of the population. But normally we're not going to have those things, okay? And so what do we do if we don't have those things? Then instead of going through and having the standard error, we're going to use an estimate of the standard error, right? So notice this, the standard error here, there's no EST next to it. This is the actual standard error for the population. So we're going to introduce the idea of a standard error estimate. And the difference between them is the standard error estimate, instead of having the standard deviation from the population in the numerator, this has the standard deviation from the sample in the numerator. And that's going to be much easier to calculate, right? So presumably we go through and we collect the sample, we can go through and we can find the standard deviation of it easily enough. Whereas if we have a very large population, we may not be able to go through and find the standard deviation for it, okay? And then everything else here, by the way, is the same. So z statistics, this is the same formula for z statistic. You'd go through and subtract these same two quantities. You take the sample mean minus the population mean, and you would divide by the standard error without this EST. That would be for a z-score. But for a t statistic or t score, you're going to divide by the standard error estimate, as we've discussed, given by this formula. A t distribution changes shape slightly depending upon the size of the sample. Okay, so this is not true for normal distributions. We're talking about t distributions. A t distribution changes shape slightly. And so because of that, we're going to introduce a new thing called degrees of freedom. So the degrees of freedom is equal to the sample size minus 1. Okay, and then at the maximum difference, the t distribution is going to resemble a normal distribution except with larger tails. Right, and then as the degrees of freedom increases, the t distribution becomes more like the normal distribution until they're indistinguishable. Okay, so this is just for your information. When it comes to going through and actually doing problems in a future section, it will be explained how to go through and calculate t values. And so, just don't get lost in the details here. This is just kind of for an FYI, and that is that a normal distribution and a t distribution are very similar, but they're not exactly the same. Okay, and so you can see the maximum difference between them is when the degrees of freedom is 1. And so you can see how similar they are. It's just the t distribution has larger tails, right? So larger means that it's further from the x-axis here, right? Thicker tails. Okay, and then if you only go up just to 10 degrees of freedom, which would be a sample of size 10, they're basically right on top of each other. And then once you get to 40, then they're indistinguishable. Okay, and so this is just an FYI that normal distributions, which is what we would use if we had the population standard deviation, it's not really that much different than the t distribution. There's just a subtle change. Now that we are going to have to take that subtle change into consideration when we go through and do problems, but it just adds one small extra step to the problems that we do in the future. Okay, so that's the video. So it just kind of introduces the idea of the central limit theorem for means, very similar to the central limit theorem for proportions. I mean, basically exact same result, except you got this t distribution, t statistic stuff that adds just this one little wrinkle which we'll take care of when we go through and we do problem solving. Okay, so that's it. See you next time.